Hello, ladies and gentlemen. Mrs. Julian is at a science teacher conference today where she's actually presenting to other science teachers about how to use Pogles in the classroom, of all things. So I will be back with you tomorrow. And today the plan is you're going to take some notes on Chapter 7 about periodicity, so periodic table trends and properties on the periodic table. And then in the second half, you will complete your Pogle that you started before the cumulative exam. Because I'm not here for the stop checkpoints, I'd like you to check with other groups. So spokespeople, you would get up and go to another group and check to see if your answers agree. And if they don't agree, have a conversation. Maybe take it back to your table and see if you can figure out a consensus about that. Please do not turn the Pogles in. They are your notes. I want you to keep them, but I will be checking them tomorrow to make sure that they are completed. Reminder tomorrow as well, the flame test mini lab is due by the end of the school day, and you have the online OWL assignments due by 11 o'clock at night. So for today, for some notes, so the second half of Chapter 7 on periodic properties. You might have already printed the slides. Great. If you have them, pull them out. If you don't have them yet, you'll probably want them, so make sure you get them printed soon. So first up is a refresher on coulombic attraction. I do want to make sure that everyone has this. Hopefully you're feeling very comfortable with this right now after the Pogle, because this very much dictates behavior on the periodic table, the idea of distance and charge and how close our particles are and the force of attraction between them. But before we jump in with ionization energy, I actually want to talk a little bit about a section of your textbook. It's actually section 21.1. And the reason I do it now is because it has to do with electron configuration, which we just came off of in the first half of Chapter 7. And it's about some odd exceptions to electron configuration, some electron configurations that we wouldn't necessarily expect based on our ability to write electron configuration. So you will be needing a periodic table for this because we are going to be writing some electron configuration. So there's an energy cost to putting two electrons in the same orbital. We know that orbitals hold 2 electrons, but electrons are negatively charged. So there is some electron-electron repulsion. Now, energetically speaking, that's a bad thing. That's why our electrons want to be in an orbital by themselves as much as possible, why they singly fill all orbitals in an energy sublevel before they go back and start doubling up. There is a small energy cost to putting 2 electrons in the same orbital due to electron-electron repulsion. Now, I know if you printed these slides, you have something else written on this slide. I'd actually like you to cross that other stuff off. I'm not going to be addressing it. And the reason is the theory has changed over the years, and that notion has kind of been disproved, or not as accepted anymore, the one that is on the slide that you have. So, exceptions to electron configuration. Chromium and copper. Now I want you to look at your periodic table, and I want you to tell me what you anticipate the electron configuration for chromium and copper to be. So chromium and copper, they're both in period 4, so we can write the abbreviated electron configuration for them. So the last noble gas that we get before we get to chromium and copper is argon. And then we go over, okay, drop down 4s2, and then count over 3d4. Remember, our transition metal section is one level lower than we think it is based on that 4s and 3d being so close in energy. So we anticipate chromium being argon 4s2 3d4, and with the same idea with copper, you count it over. It's 5 over. You anticipate copper being argon 4s2 3d9. That's what you would totally expect based on how you know electron configuration in the periodic table work. Ha ha ha! You'd be wrong! This is actually not the electron configuration of chromium. It is not the electron configuration for copper. Instead, the electron configuration for chromium is 4s1 3d5. And the electron configuration for copper is 4s1 3d10. Which begs a really big question of why? Why is this doing something that we don't anticipate that we don't expect it to be doing? It has absolutely everything to do with the fact that I had you pay attention it was a little while ago now, to that 4s and 3d sublevels. The fact that they are so close in energy to one another, that they are truly almost virtually the same energy. The fact that they're so close in energy, we actually tend to only see this with S and D, meaning P, the P sublevel, is way too far removed energetically from 3D. So this is something that we only see in transition metals because of this close energy difference for S and 3D. So let's think about the chromium. If you think about 4s2 3d4 versus 4s1 3d5, if we were to write that out with orbital notation, right, I would have 4s, the one orbital in 4s, and then 1, 2, 3, 4, 5, the 5 orbitals in 3d. If I have 2 electrons in 4s and then 4 electrons in 3d, like that, they would be spread out, right? But remember, what this is saying is that these 2 sublevels are almost the same energy. So, if they're almost the same energy, then why would you have electron repulsion here? Because you have 2 electrons in the same orbital, when you have an empty orbital that's almost at the same energy level, not significantly higher, almost at the same energy level. So you can take this electron and kind of promote it, put it up there. So when we make that change, we get the observed electron configuration of 4s1 3d5, and this way there are no electron repulsions occupying the same orbital. And this is actually slightly energetically more favorable for the chromium, for the chromium atom. We say it promotes the 4s electron to an empty 3d orbital. Now, in the case of copper, the difference is 4s2 3d9 to 4s1 3d10. We no longer have half-filled orbitals in the case of copper. We have completely filled ones. So we've got 4s. We would think it would be, 1, 2, 3, 4, 5, 6, 7, 8, 9. But instead, what we see is 4s1, 3d10. That we'd rather put this, instead of having the electron repulsion in 4s, we rather have that electron repulsion be in 3D instead. And I think part of the theory for why this happens, and it is a theory, people are kind of trying to look at this, is that we will get slightly less repulsion in the 3D sublevel due to the various shapes, the different shapes that the orbitals can have. And again, considering that these guys are almost the same in energy, let's have that electron repulsion in the D-shaped orbital rather than the spherical S-shaped orbital. So there are theories as to why that is, and that's still being worked out. So these are some exceptions in electron configuration that I did want to sort of make you aware of. Now, some other exceptions with electron configurations also have to do with transition metals, and they have to do with when the transition metal becomes an ion. Transition metals, because the S and the D sublevels tend to be so close in energy to one another, that once they start losing electrons, once the metals start becoming ions, just put this all up here, the electrons start to rearrange themselves, and we actually get an energy shift. This means that as soon as we have an ion for a transition metal, like zinc, the outermost electrons aren't necessarily where you think they would be. Now, we know that the electron configuration for zinc would be argon 4s2 3d10, right? Hopefully we have no problem with that. Now, you would think that if you were to lose 2 electrons, you would probably be losing them off of the 3d10, and this would go to something like 4s2 3d8. But it does not. That is not what happens. Instead, what happens is as soon as we start losing electrons, now the atom, the ion I should say, will start to shift its electrons to put all the remaining electrons in the d sublevel. And this is true of all transition metals. All of them. All of them. As soon as they become ions, we actually get a change in the energy of the D sublevel. It's 3D in the case of zinc. It could be 4D if you're looking at anything from period 5. It could be 5D if you're looking at transition metals from period 6. By taking the outermost electrons away, instead of the S and the D being close in energy to one another, right, the S and the D being close in energy, almost the same energy, we get a change to S actually being lower. I'm sorry, I drew that backwards. S becomes higher energy because it is an energy level higher, right? It's 4S, and then we get 3D, which is lower in energy. So the ion would prefer to have its outermost electrons, as always, in the lowest possible energy sublevel. As soon as we get some electrons removed, we will change the force of the attraction that the nucleus has, because now there's less stuff on the outside, and we actually do get a shift in the energetics of those sublevels. So this means that the electron configuration for all transition metals will involve their d electrons staying intact and their s electrons being gone. It's not that we pulled from the s first, it's that we took electrons away and then the metal rearranged where the electrons were to put everything back in the d sublevel. So that's a little weird minutia that comes up. The AP has this really weird thing where they actually really like to ask you what electron configurations of transition metal cations are, so I'm making you aware of that. Don't write them with the s electrons still there, because they're not. They're actually gone. Charge interactions in an atom. This is, again, talking about coulombic attractions and things that are going to be very important for us. It's very important for us to consider anytime we're talking about an electron in an atom, how close is that electron to the nucleus? Because things change the closer that electron gets. The force of attraction that electron has for the nucleus very much depends on its relative distance to the nucleus. In addition, the force of attraction that an electron will feel will very much depend on how many protons are in that nucleus and how strong a pull they're feeling. But it's not just about number of protons, and that's what this next slide, effective nuclear charge, is really getting at. Effective nuclear charge is actually something that technically can be calculated. Now, we're not going to be calculated, so don't worry about trying to memorize this formula. Trust me, you don't need to know it. But it's basically a way of saying this thing in bold right here. It says that all electrons in an atom do not feel the same pull from the nucleus. That's essentially what this is saying, what effective nuclear charge is getting at. And we have this little formula here. It says effective charge, that's ZEF. It can be calculated if you take how many protons you have in your nucleus, so that's Z, so that's your protons total, but then you subtract the average number of electrons that are in between the electron that you're looking at and the nucleus. This is saying that an electron on the outside that has, let's say, 3 energy shells between it and the nucleus is not going to feel a very strong pull from that nucleus because all those other electrons are getting in the way. They're blocking, essentially, the nucleus from being attracted to that absolute outermost electron. Other electrons in the atom matter, and they change the effect that different electrons can feel from the nucleus. So the nucleus is not experienced the same way by all the electrons in the atom. And that's what effective nuclear charge is saying. We call this shielding. We say that the outermost electrons are shielded the most from the nucleus, that they're not feeling the same pull because the other previous shells are shielding them. They're not allowing that positive charge to kind of break through. And we see that as our distance from our nucleus increases, as your electron becomes further and further away, the number of electrons that are between your electron and the nucleus, they go way up, and therefore your effective charge, how much that outermost electron is experiencing the charge of the nucleus, it goes way down. with that in mind, orbitals between atoms are not the same because of things like shielding, because of things like different numbers of electrons in the different number of protons in the nucleus. The more positive your nucleus becomes, the smaller the orbital in question will become. And this is true for all orbitals. So I could say, let's consider a 1s orbital, let's consider a 2p orbital, let's consider a 4d orbital. And for all of them across the board, even with shielding, the more positive the nucleus becomes, the smaller the shape of the orbital becomes. They'll have the same shape. For example, sodium 1s orbital absolutely has the same shape as a hydrogen 1s orbital, but they are not the same size. Now, if you think, notice here that I'm not saying energy level 1, I'm being very specific. I'm specifically referencing one orbital in particular, and that's the 1s orbital. Both of them are spherically shaped, and I'm referencing the very first orbital that gets filled for any atom, 1s. So this is the first one. 1s, regardless of which element you're talking about, will always be closest to the nucleus. And notice here that I am not talking about atomic radius, because atomic radius is between your nucleus and your outermost energy level. I am not concerned with that in this case. I am only thinking about 1s and 1s alone, and that is it. Just orbital 1s, just that very first orbital that gets filled up, the one that is closest to the nucleus. The one that kind of doesn't care, the one that's going to do the shielding, the one that is not shielded. This can experience the nucleus the best out of all of them. So you want to then, if you think about the size of that 1s orbital, it's all down to protons. Sodium has 11 protons in its nucleus. So that 1s orbital that's right next to that nucleus that contains 11 protons is going to feel a certain pull. We compare that to hydrogen. Hydrogen only has 1 proton in its nucleus. We're comparing the exact same orbital in each one. We're not comparing the furthest orbital, we're comparing the closest orbital. Which orbital will be larger? Which orbital will be smaller? Please don't tell me that the sodium orbital you expect to be bigger, because it won't be. The 1s orbital in sodium is significantly smaller than the 1s orbital in hydrogen, because that orbital that's closest to the nucleus for sodium is experiencing a pull of 11 protons on it. So it's getting pulled in super, super tight. Versus hydrogen, that 1s orbital in hydrogen is only experiencing the pull of 1 proton. So it's not as close to the nucleus. And anything with more protons than sodium, like, oh, I don't know, cesium with 55 protons, its 1s orbital is going to be crazy smaller than sodium's 1s orbital. So we can compare the same orbital in different elements. And it's not a question of atomic radius. It's not a question of number of electron shells. It's a question of how many protons are in that nucleus and what impact they're going to have on the size of the orbital. So that's what I wanted to get through for today. So I'd like you to move on and work on the periodic trends review POGL. And again, we've got some stuff due tomorrow. If you have finished the POGL, you can use a laptop and work on the OWL assignment. You can also make sure your mini lab is done and turned in.